Greetings, fellow physicists, and welcome back to Conceptual Physics and Chapter 7, which of course concerns energy. So let's talk about energy. What is energy? Energy is the ability to do work. But what is work? Well, work is what's done when you expend energy. And unfortunately, it's a kind of a goofy circular definition, but it goes something like this. Imagine that your job is to lift bags of concrete from the ground onto a building that is being built. Now, if you had to lift some bags of concrete up and take them from the ground floor up to the second floor, would you do more work or less work if you carried 2 bags up to the second floor instead of 1? Obviously, you'd be doing more if you carried 2, right? If your job was to carry a bunch of bags up there, you'd get it done half the time if you could carry 2 of them. So, how much force you have to exert, because obviously 2 bags have a greater mass, right? And so you have to overcome a greater force of gravity. Therefore, how much force you have to exert is one of the factors in defining what work is. One of them is force. Now, how about if you carried a bag of concrete from the ground floor, not up to the second, but up to the 3rd floor? Would you be doing more work? Well, yeah, you carried it farther, right? So the distance is also a factor. Thus, work we usually say is force times distance. What are the units of work? Well, force has units of newtons, right? Work has units of force times distance. We got newtons times meters, right? But a newton, if you remember from F equals ma, newton is a kilogram times meter per second squared. So that's a newton times a meter. So kilograms times meters per second squared times meters, that's kilograms times meters squared per second squared. That is a unit that we call the joule. Joule for James Prescott Joule, the person who figured this out. Now, the rate at which work is done is called power. And power is work per unit time, how quickly you do work. Work, of course, has a unit of joules. Time, of course, has a unit of seconds. So a joule per second is your SI unit of power, or watts. Now, back to energy. Energy allows us to do work. There are plenty of kinds of energy. There's chemical energy, like what you have in, say, a lead-acid battery. There's thermal energy, like from heat or a fire, something like that. There's electrical energy, right? The thing that we're using currently right now to power our computers. But for now, let's just focus on the very basics. There is potential energy, say in the form of the energy that's stored in a bowstring if you draw your bow, for example. Or like in a spring, right? If you compress a spring, then it's going to store energy in it. The same thing if you pull a spring outward, it's going to store a certain amount of energy in it, right? And when you release it, it's going to try to restore itself to equilibrium. There's also gravitational potential energy. Like if I lift this pen up, the higher I lift it, the more potential energy it has, right? Now, if I drop this object from rest, from a non-zero height above the floor, it has the potential to do work on the falling object, right? So what affects how much gravitational potential energy an object has? Well, obviously, if I raise an object up, it has more gravitational potential energy, right? So, we've got potential energy in the gravitational sense, right? One of the things that's going to determine how much potential energy an object has gravitational potential energy, that is the height, right? Well, what about if I drop a really heavy object, like a book, right? If I take this book and I drop it, and I take the pen and drop it, which one is going to hit the ground with more energy? We can very much hear the difference, right? This barely makes a noise. But the book... So then mass is a factor, right? Now we're missing one more important thing, and that, of course, is the motivating factor, what is causing things to fall, causing things to have gravitational potential energy to begin with. And that, of course, is gravity itself. Thus, gravitational potential energy is mass times gravity times height. And of course, if you were on the moon or on Mars, somewhere where surface gravity acceleration is a little bit different, you would have a different amount of gravitational potential energy at a given height. What are the units of energy? Well, those should have the same units as work, right? We've got mass is kilograms, acceleration is meters per second squared, height is in meters, kilograms times meters per second squared times meters, that's kilograms times meters squared per second squared, or joules, just like we would expect. As a matter of fact, you can sort of think of gravitational potential energy as height times weight. You'll notice mass times gravity, that's the weight of an object, right? So the gravitational force essentially times the height will tell us how much gravitational potential energy an object has. It is important to note that it doesn't matter what path you take to raise an object. The amount of work done is still the same, only the change in height is important. If you move an object horizontally, it doesn't do any work against gravity. If you move an object diagonally up to the second floor, the change in height and therefore the work done against gravity is still the same as if you raised it straight up. If you let the object fall, gravity does the work. We say that this change in height is path independent, and therefore gravity is what we call a conservative force. Alright, let's put just a couple of numbers in here. Let's say that you lift a 100 Newton block of ice up by 2 meters. How much work did you do? Well, 100 newtons times 2 meters, that's 200 joules, right? But what if, instead of trying to just take this 100 Newton block of ice and lift it straight up 2 meters with a rope and pulley system or whatever, what if instead you decided that you were going to push it 4 meters from the bottom of a ramp up to the top of a ramp? Well, we're just going to assume that this ramp has a 30-degree incline. And due to the geometry of the situation, I'll spare the details, but this height is still 2 meters. And so we're actually only lifting it 2 meters anyway. What does that mean? Well, while it only requires a force of 50 newtons to push this block up the ramp, and it would take a force of 100 newtons to lift it straight up into the air, we're still doing the same amount of work. 50 newtons times 4 meters is still 200 joules. And so the path really doesn't matter. It's really just how much progress we make against gravity. That's going to tell us how much potential energy we have. Obviously, not all energy, is potential energy. There is, of course, the energy of motion, what we call kinetic energy. We say kinetic energy is based on a couple of things. Kinetic energy, we usually say, is dependent upon the mass of the object, obviously, but also upon how fast it's moving. Now, what are the units of kinetic energy? As you might expect, we better get joules out of this, right? Okay, so we've got 1/2, that has no unit. Mass is kilograms. We got velocity squared, that's meters squared per second squared, right? That's joules. So we're good. Note the square and the velocity. If you're traveling in your car at 30 kilometers per hour, you will require a certain amount of stopping distance, right? From where you hit the brake to where you finally stop. Before your brakes can do enough work, remember work is force times distance. You're going to require a certain amount of stopping distance based on your velocity, right? But what if you're moving 3 times as fast at 90 kilometers per hour? You have 3 times as much kinetic energy, right? Or I'm sorry, you have 9 times as much kinetic energy, right? Because 3 squared is 9, right? And this is based on the square of the velocity. Thus, you would have 9 times as much kinetic energy, meaning you would have to do 9 times as much work, and if your brakes can only apply a certain amount of force, you need 9 times as much stopping distance in order to stop your car. Now this is a really important, this is a very important consequence, and that of course is this. We said that the work done is equal to the kinetic energy lost, right? That means that work is equal to change in kinetic energy. This is called the work energy theorem. Essentially, if you want to speed something up or slow something down by changing the amount of kinetic energy it has, you can do work against or on that system in order to change the amount of kinetic energy it has. Now the important part. We said that when we were studying chapter 6 that there are symmetries in nature from which arise conservation laws. And energy is a conserved quantity, and that should give rise to another conservation law, the law of conservation of energy. What does that mean? It means that energy can neither be created nor destroyed. It can only change forms or move in between systems, something like that, convert from one system to another or one kind of energy to another, but the total amount of energy in the universe more or less stays the same. If I take this pen and I raise it up, it's going to gain some potential energy. When I let go, it's going to fall. It's going to lose its potential energy. But what happened to that potential energy? It turned into kinetic energy, right? The farther it falls, the faster it moves, right? So as it loses potential energy, height, it's going to gain kinetic energy, velocity. But what happens to that kinetic energy when this pen hits the chair? Well, did we hear it hit the ground? So some of that energy became sound, right? If I drop this pen 100 times in the same spot, in exactly the same spot, over and over and over and over and over, would this spot be warmer? Well, yeah, of course. Some of that energy is going to be converted into heat, right? It makes a lot of sense. What happened to the rest? Well, the chair vibrated a little bit, right? That vibrated the floor, that imparted some energy into the foundations of the building and then to earth and so on. So the kinetic energy was absorbed, it went from one system into another, and so on, but it was not lost or destroyed, right? It only moved in between systems. Okay, let's talk a little bit about machines, shall we? Does everybody know how a crowbar works? Let's say that you have a 1 meter long crowbar. Okay? So the crowbar generally has like a little spiked bill at the end here. You know, sometimes there's like a little handle for a lever here. And let's say that this overall is 1 meter long, and you manage to wedge 1 centimeter into a door frame. Whoops. Excuse me one moment. Almost lost the pen cap. So, let's say you manage to wedge 1 centimeter of a crowbar into a door. So you can try to break it open to avoid being eaten by a horde of zombies in a zombie apocalypse, let's say. Now the bent part right here at the corner, we call this the fulcrum, because this is essentially a lever, right? And the crowbar works by essentially rotating around that point. You pull on this end goes further into the door. And if you do it right, you just might be able to pry the door open and save yourself from being eaten by a bunch of flesh-eating zombies. But how much force can this produce? Well, the law of constant energy states that you should be able to get the same energy out as you put in. And of course, work equals energy, so the work output should equal the work input. Work input, of course, is force times distance in, and the work output is going to be force times distance out. What I mean is, you're going to apply a force here, and it's going to apply a force out. This force is going to be applied along this huge lever arm, essentially the entire length of the crowbar. The output force is going to be applied just along this tiny little length, the part that's wedged into the door. Now, let's say that the force input is something like 10 newtons. That's not super strong, right? That's that's like holding up a weight of 2.2 pounds. That's how much a force of 10 newtons is. Okay? Now, the lever arm here is going to be 0.99 meters or 99 centimeters, right? So if you apply 10 newtons of force along this 99 centimeter lever arm, you're going to do 9.9 joules. Ninja. Oh, Ninja. Can't block that way. You're going to do 9.9 joules of work on the crowbar. The crowbar then, of course, is going to do a certain amount of work against the door. But how much is that? Well, it's not going to move very far, right? We're talking about 1 centimeter. And so, in order for this to work, it has to apply an incredibly large force. Make 9.9 joules. Long story short, if you can apply 10 newtons of force, not a whole lot, along this tremendous lever arm that's 99 times longer than the amount of crowbar that you wedge into the door, you're the force that you're going to apply is going to be multiplied 99 times. Now that might seem to break the laws of nature, but honestly, you're moving this huge thing a great distance, and this only moves a tiny little bit, so it applies a tremendous amount of force. 990 newtons, that's almost 1,000 newtons compared to the 10 newtons of input force that you put on this thing. That's the difference between holding up a 2.2 pound weight and literally the bite force of a crocodile. And that makes the crowbar pretty useful. Or the jack that you use to jack your car up so you can change your tire, things like that. You can't lift a car on your own, but the jack definitely can, right? And that's also why you crank the jack a pretty good distance every time, but it only moves like a few millimeters, and you have to keep jacking it and jacking it and jacking it in order for it to lift the car an appreciable distance so that you can take the wheel off and put the spare on. There's a contraption called a block and tackle, which is essentially like one length of rope along several pulleys, so that when you pull it a great distance, and it only moves the object up just a little bit, right? But you're able to apply a greater force by putting in greater effort and pulling the rope a longer distance. Now, most machines aren't 100% efficient. The crowbar is pretty good because it's basically just a lever. Levers only usually lose about 2% of their energy to heat and friction. And so we would say that the efficiency of the crowbar is something like 98%. That means we have to define efficiency this way. Efficiency is defined to be the energy output divided by the energy input. If we get 98% out over 100% in, it's 98% efficient. Most of our power plants, for example, are something like 33% efficient, losing about 2/3 of their energy in form of the heat generated by burning fossil fuels or something along those lines, the things that are wrecking our living environment, right? Destroying the earth. The internal combustion engine, right, with the gasoline burning engines that are in most of our cars, are about 10% efficient once the rubber actually hits the road. The engine itself is maybe 30% efficient, but it's going to lose maybe 2/3 of that trying to convert all that energy from rotation inside the engine into rotating the wheels. And so cars are actually not very efficient at all. Now the book talks about different sources of electrical power generation, things like solar panels. What the book doesn't tell you about solar panels is that the photovoltaic cells that we use to make solar panels are bad for the environment. And they're even worse for us. They're toxic to human life. They may not be contributing to climate change so much, but we're not, as a species, very good about disposing and recycling dangerous chemicals and materials. We end up just throwing a bunch of stuff in a dump and it pollutes the earth, and it's pretty gross. Now that doesn't mean we shouldn't use solar power. We should. We absolutely should use every kind of renewable energy source that we can and get away from using internal combustion engine vehicles and burning fossil fuels, because only then can we stop polluting our environment and maybe, get our environment back a little bit. Now the book talks about water power and wind power. Wind power, of course, things like windmills, that the wind, of course, turns the windmill blades, and that generates electric power, right, by turning a generator. And I'm sure you'll agree that's pretty clean. That's pretty good. Portugal built a bunch of turbines near their coast so that when the tide would come in and when the water level would rise, it would turn some turbines, and when the tide would go out, it would turn the turbines back. And that seems like a good idea, and indeed, it's not a bad idea, of course, but it takes weeks for the tides to cycle and the wind isn't predictable, and as a result, generally these kinds of power aren't enough to power, entire cities. The things that, the amount of power that we as a species use is kind of a lot. The book also talks about using hydrogen as a fuel, and burning it does indeed generate a good amount of power, and the byproduct actually is harmless, completely and totally. So if you burn hydrogen, right? Elemental hydrogen is H2. Basically, when you burn something, you add oxygen to it, right? You burn it. Now, in order to balance this equation, we're going to have to do this, because what we're going to end up with is, believe it or not, when you burn hydrogen, your waste product is water. However, making pure hydrogen is difficult. The book talks about running a current through water to separate the hydrogen and oxygen from the water in order to make hydrogen and oxygen gas. But that requires a current to begin with, like the current from a battery. And that means you already need a power source. If you want to separate it from hydrocarbons, you're going to release things like carbon dioxide. And carbon dioxide is a greenhouse gas. And greenhouse gases are the things that are causing climate change. And if you don't believe me, and if you think this is my political agenda or whatever kind of nonsense, please allow me to explain the science to you. If you don't believe me, you can always go to climate.nasa.gov. Just in case you feel like you want some more information, go to climate.nasa.gov, and they've got all the stuff that I'm going to tell you and a whole lot more. Now, I've included a link to a video of water expanding as it heats up, because that's what happens. Mostly, just about all substances, when you heat them up, they expand. That's why we say heat rises, because as the gas or whatever that you have that gets heated up expands, it becomes less dense, gravity has less of a hold on it, and of course it rises in comparison to the matter nearby it. But in any case, invariably, light from the sun warms the earth. Some of that light bounces off the atmosphere or the clouds, and some of that makes it down to the surface and warms us. So, let's say this right here is the surface of the earth, right? And then out here, we have like some atmosphere, some clouds or whatever. Hydrogen, oxygen, that kind of thing. So some of the light is going to get down to the earth, and some of it is going to reflect off, right? Now, the light that bounces off obviously is going to be radiated off into space, but the stuff that gets down to the earth is going to heat the earth, right? And if you don't believe me, all you have to do is step out into the sunlight during the day. Obviously, the light from the sun is going to warm us, right? Now, some of the light that hits the surface is going to bounce off, and some of it's going to go into space, but some of it is going to be reflected by the atmosphere and come back down and warm the earth up, right? Now, if we have greenhouse gases in our atmosphere, it's going to make this thicker, right? And so more of the light that gets reflected off of the earth is going to be reflected back down to the earth and back down to the surface and cause even more heating. And that is why the world is getting warmer. There's this thing that we call the temperature anomaly, which is a measurement of the global temperature average. And we've known for decades, for many decades as a matter of fact, that this is very closely tied to the concentration of carbon dioxide in our atmosphere. Now, if this is true, what's supposed to happen when the climate changes? Obviously, the world is going to get warmer, and that's going to wreak havoc, with our weather systems, but we'll come back to that. But what about the polar ice caps? Are they melting? Yes, indeed they are, and as a matter of fact, we now have a shipping route that goes through the North Pole, and that would not be possible if the North Pole were still completely frozen. Now, if the ice caps melt, are we going to drown? Well, don't freak out yet, okay? If you have ever had like a soda with ice in it, when the ice melts, does it ever spill over? No, of course not. That's crazy, right? Ice is less dense than water, so when all of the ice melts, the water line is actually going to go down a little bit. But once all of the ice has melted, right? Once all of the ice in the cup is melted, then the water in the cup can heat up and expand, and then maybe it'll flow over. So the world isn't going to drown just yet, not right away at least. However, do you know what's happening in Venice, Italy? It's going under because the sea levels across the Earth are rising. The polar ice caps are melting. That's releasing more free water, and the water that's away from the polar caps are getting warmer, right? The water, especially near the equator and the tropics, those can get heated up. That can get heated up a whole lot. If you know anybody who's an experienced fisherman, they'll tell you that the coastlines also are receding, and that has been a gradual thing that we've really taken a notice of over the last 50 or so years. The global temperature average has jumped about 1.7 degrees C, and degrees C, of course, is the SI unit of temperature, not degrees F. We use degrees C for Celsius or centigrade. The last time the carbon dioxide concentration was this high was about 3 million years ago, and at that time we had a temperature anomaly in between 2 and 3 degrees. Right now we've got 1.7 degrees C temperature anomaly. Last time it was this high was between 2 and 3 degrees C. And at that time, the average height of the seas across the world rose about 15 to 20 meters higher than they were in the pre-industrial era of our history. That means we are projected to have our sea levels rise about, well, they're going to rise a lot, because in the next few decades, we're probably going to see a temperature anomaly of close to about 10 degrees C. Now, if you look in the comments or on the Chapter 7 lecture page, you'll see the video the link to the video that I posted about what happens to water when it gets heated up. Obviously, it's going to expand. And if we heat up the water, essentially the water level will rise. Essentially, if we keep heating the world up, then the oceans are going to rise. And that is what is happening right now. The seas are rising. Now, basically about 98% or so of the world's scientists agree that this is what's happening. This is fact. The other 1.7% or so generally have ties to the oil industry or something along those lines. And they're all full of garbage. Don't let them lie to you, okay? Don't believe their nonsense. They'll try to tell you crazy things like volcanoes and other sources of natural carbon dioxide are greater than human output, and that's not true. We produce about 60 times what nature does. Climate change is no accident. This is not part of some cycle. We are destroying our own habitat, our own living environment. These naysayers will probably also try to tell you crazy things like global warming isn't real because our winters are getting colder. First of all, they are not. In 2015, I believe it was, we had a really, really short winter. It was shorter than warmer than the last one before that. And then in 2016, we had a shorter and warmer winter. In 2017, we had one that was shorter and warmer than that. And so on. And our winters have continued to get shorter and warmer. But we do have really, really crazy weather patterns. About 10 years ago, you would have thought that an 80-degree day at the beginning of February was crazy talk. That never, never, ever happens. Oh, look, it's Lucky Meow. Oh, Lucky Meow. Can you tell us about climate change, Lucky Meow? In any case, we have to be really careful that we don't confuse weather patterns with climate change. We are having really crazy weather patterns because crazy things are happening, like the polar ice caps are melting. Now when the polar caps melt, what's going to happen is all the ice at the polar caps is going to melt, and cold water is going to rise, or cold air, excuse me, is going to rise up from the cold water above the polar ice caps. And what's going to happen as a result of that is there's going to be more cold air at the poles. Now there's already tons of cold air at the poles, at least currently, because they're mostly still frozen, right? But say at the North Pole, as the polar ice cap continues to melt, it's going to release more cold air into a place where there's already cold air, and that cold air is going to have to go somewhere, right? It's going to have to get pushed out of the way to make room for more cold air. Now, if you were a bunch of cold air, would you try to go out over the ocean where there's constantly waves lapping against you and lots of wind, right? Tropical storms, hurricanes sometimes, what they call typhoons in some parts of the world? No, probably not. Probably you're going to take the path of least resistance and go down out over a flat land mass that's going to offer you much less resistance, right? And that's why in 2014 we had a bunch of crazy snows, because the cold air from the melting polar caps drifted down over North America and snowed all over us. If you look in the comments or on the Chapter 7 lecture page, there's a nice image of, this is from NASA Goddard. You can very clearly see the cold air coming straight down over the North American continent from the North Pole. Very simple. In any case, the real fact of the matter, the truth is that the world is getting warmer. And that's why we had dry Octobers and Septembers and Novembers with lots of fires in them recently. And that's where Santa Rosa burned down a few years ago, if you remember. And so it's changing. Our climate is changing very quickly. And if we don't do something to stop it, we're in big trouble. So what can we do about it? Well, for starters, we have to break our dependence on fossil fuels. So what can we do? Well, internal combustion engines are still our #1 polluter, and so we need a way to generate power without causing damage to our environment, something that we can use to replace the internal combustion engine. So if you get an electric car, that's going to help. But also, we need to figure out a way to generate power for these electric cars without burning more fossil fuels. Does everybody know what we use to generate power here at PG&E in California? Well, it says it right in the name, Pacific Gas and Electric. Mostly they burn natural gas and shale oil and things like that. And we're going to have to figure out a way to break this dependence on fossil fuels in order to generate power without causing further damage to our environment. How? Well, once upon a time, a guy named Nikola Tesla tried to get power from the Earth's magnetic field. So that might help. Yes, we're in a bad state. Yes, things look bleak now. But as long as we're still here, we still have a chance to change. We can still make a difference. We can still save ourselves and our environment. If you remember, we had a problem with our ozone layer once upon a time because we were releasing a lot of what we call CFCs, or chlorofluorocarbons, things like the coolant Freon that we used to use in air conditioning, things like hairspray, all those things. And as soon as we stopped polluting the atmosphere with CFCs, the ozone layer started to fix itself. That means it's not too late. As long as we're still here, we've still got a fighting chance. So, your homework for this week is to go out and fix it. Bring an end to this crazy climate change. Do your part, do whatever you can. Think globally, act locally. Try to make a difference. In any case, I hope you've enjoyed this lecture. I'll see you again soon for Chapter 8.